Hello, young chemists. What is up? This is Mr. Rosen. Today we're going to talk about the ideal gas law. It's the fourth of the gas laws in our unit. The ideal gas law also deals with pressure, volume, and temperature, but introduces a couple of new things that we haven't seen before. So we're going to work through a couple of example problems. The ideal gas law not only solves or allows you to solve for pressure, volume, and temperature, but it also introduces two variables which we haven't used before. One's actually not a variable, one's a constant, R. But the ideal gas law here is written as PV equals nRT. PV equals nRT. You could probably anticipate P is pressure, V is volume, T is temperature. What's maybe new to us is N and R. The lowercase n stands for number of moles. So moles of gas. This equation actually allows us to consider and solve for how much gas is present, how many moles of gas is present. Hopefully it would make sense to you that if you have a container where the volume is fixed and the temperature is held constant, if you put 1 mole of gas in the container, it would exert some pressure inside the container on the container walls. But if you had an identical container at the same temperature, same volume, and you put, let's say, 2 moles or 3 moles of gas in that other container, there would be more gas particles inside bouncing around, which means they would be hitting the walls more frequently, and the pressure in that other second container would be higher. So the amount of gas you have present influences other variables like pressure. Now, R is the universal gas constant. R is 0.08206. Okay, in some textbooks or worksheets, you might see it written as 0.0821. That's okay. In my class, we're using this number just to have another significant figure. But you'll get very, very similar results with both. As it says here, you need to know what R is. And the units on R are liter atmospheres over Kelvin mole. You need to have all of the other measurements in the equation with the same corresponding units as this. Okay, so we're going to have, PV equals nRT. The pressure needs to be in atmospheres. The volume needs to be in liters. The temperature needs to be in Kelvin. And our amount of gas, it can't be in grams of gas or something. It needs to be in moles of gas. So we might have to do conversions in order to use R in the ideal gas law. So the first question says, if Mr. Rosen had 82 liters of neon gas held at a pressure of 3.2 atmospheres and a temperature of 255 Kelvin, how many moles of gas do I have? So I have temperature, volume, and pressure. I can now solve for the amount of gas that I have, the number of moles of gas. And just to check my units, volume is in liters, which is good. Pressure is in ATM, which is good, and temperature is already in Kelvin. So I actually don't have to convert any of these. I'm just going to first take a minute to identify each of the variables. So pressure is 3.2 ATM. Volume is 82.0 liters. And I am solving for N, right? I don't know what N is. That's number of moles. That's my question mark. R is the universal gas constant, 0.08206 liter atmospheres over Kelvin mole. Okay, again, that's just the unit on R. And then T is our temperature, which in this case is 255 Kelvin. So I don't need to convert any of these numbers. I can just simply plug them into the ideal gas law, which again is PV equals nRT. So let's plug them in. Step 2, plug each variable into the equation. So I'm going to just turn that into a 2. Sorry about that. So 3.2 ATM. That's our pressure, 3.2 ATM. Our volume is 82 liters. That's PV equals N R and then we have T, which is 255 Kelvin. All right? So PV equals nRT. Step 3 is to isolate the desired variable, which in this case is n. It says by dividing both sides of the equation by the two variables on the given side of the unknown. Well, in this example, we have two variables on the given side of the unknown, but if it was on the other side, then you would just have one. So we could just say by the variable or variables. So to get n all by itself, we need to divide by the other stuff that's on that side. So dividing by r and t, really this equation right here, we're just rearranging this to solve for n. So n equals PV over RT. Okay, that's really what we're going to end up doing here. But to get n all by itself, we'll divide by 0.08206 times 255 Kelvin. These will both cancel out, so this cancels and this cancels, and we are left with just n on the right side of the equation. Okay, but whatever we do to one side of the equation, we're going to do to the other side of the equation. So this side has to get divided by RT, 0.08206. That's liter atmospheres over Kelvin mole. And we have 255 Kelvin as our temperature. So if we take pressure times volume divided by R times T, temperature, we will get N. Now, one thing that students tend to mess up on here is when they plug numbers into their calculator, what students often do is they go, okay, 3.2 times 82, and they get some number, right? And then they go divided by 0.08206 times 255. Enter. Now, this is the wrong answer. That's wrong. And you might be thinking, hold on, Mr. Rosen, I just saw you type that in. It says this times this divided by this times this, and you did that. But the problem was what I actually did on the calculator was I took these two numbers and multiplied them. I then divided it by R, and whatever that number is was then multiplied by 255. And that's not what you want to have happen. Okay? You want the product of the two numbers on top to be divided by whatever the product of the two numbers on bottom is. So this is an order of operations thing in your calculator. Okay, so 3.2 times 82, okay, we get that number, but this time we say divided by, open parentheses, 0.08206 times 255, close parentheses. So now it's taking the product of the two numbers on top and dividing it by the product of the two numbers on bottom, and we get that, which is about 12.5. And in terms of units, right, N is number of moles, but if you look at our units here, liters is on top and liters here. This is, or sorry, atmospheres and atmospheres will cancel. Liters and liters will cancel. and then Kelvin and Kelvin will cancel, and the only unit is left is moles. All right. So that's an ideal gas law problem solving for n moles. All right. Once you isolate the variable, that is arriving step 4, arrive at your answer. Let's do a couple more, and we'll pick up the pace a little bit on these ones. So question number 1. Says a 3.8 mole sample of gas at a pressure of 4.6 atmospheres and a volume of 12 liters will be at what temperature? So in this one, we're actually given moles. So we're not solving for moles, we're solving for a different variable this time. So just like always, I am first going to identify what I do know and what I don't know. What are each of the variables? Okay, so the pressure is 4.6 atm. The volume is 12 liters. N is the number of moles, so that's 3.8 moles. R is the same number every time. The universal gas constant, 0.08206 liter atmospheres over Kelvin mole. And T is the unknown. Temperature is what we're solving for. So let's plug them into the ideal gas law. PV equals nRT. Okay. So it's 4.6 atm times 12 liters equals 3.8 moles times R, 0.08206, times T. We're solving for T. Okay. So we need to get T all by itself on one side of the equal sign. All right. And really just, again, back to here, if we were to solve for T, to get T by itself, right, we divide by NR on both sides. So really, we're just taking this and rearranging it so that T equals PV divided by NR. Okay, that's what we're going to end up doing here. So we need to solve for T. To get T all by itself on one side of the equal sign, I'm going to divide by the other stuff on this side, 3.8 moles times R, 0.08206. If we do that, these both will cancel and leave us with T on the right side of the equation. Okay, but whatever we do to the right side, we're going to do to the left side. So this side has to get divided by 3.8 moles times 0.08206. Again, atmospheres is going to cancel, liters is going to cancel, moles is going to cancel, and the only thing that's left will be our temperature in K. So if we do this, 4.6 times 12, okay, whatever that is, divided by the product of 3.8 times R. If we do that, our answer will come out in Kelvin. So just to, again, show you on the calculator, 4.6 times 12, okay, you get this number. That's divided by, open parentheses, sorry about the glare, open parentheses, 3.8 times 0.08206, close parentheses, we get 177, okay, 177, which is the temperature in Kelvin. Now let's do something a little different. I want to solve for a variable on the opposite side because this was just like pretty close to the last one, but last one we had temperature and not moles, but the way that we divided was the same. This last problem here is you are given moles, temperature, volume, but you don't know the pressure. So P is unknown. Volume is 84.8 liters. N is 12.2 moles. R is the universal gas constant. And T is 67.0 degrees Celsius. Now, we're going to plug these all into the equation. So the equation again, PV equals nRT. And we're solving for P, right? So if I wanted to solve for P, I would divide by V on both sides. So this, if I was to rearrange it, P would equal nRT divided by V. Okay, so I'm going to do this, but let's plug all of our numbers in here. So we have P, V equals N, R T. Now, notice this, okay? Temperature is in Celsius. Look at the units of R, okay? L, that's volume, is in liters. Our volume is in liters. That's good. Mole for amount, mole for amount. The temperature unit is Kelvin. So if we're going to use R, all of the other measurements have to have corresponding units. So we can't put Celsius into this equation, okay? We're going to turn this into Kelvin by adding 273 to it, okay? Again, remember, temperature in Kelvin is equal to the temperature in Celsius plus 273. So if we take our temperature, which is 67, plus 273, we get our temperature in Kelvin, which is 340 Kelvin, okay? 340 Kelvin. That is what we're going to use for our temperature, 340 Kelvin. It's a very important step. A lot of students mess that up, and they get the problem wrong. So now, this case, we have everything on the right side. In the last two problems, we've been solving for something on the right side, but in this case, we have to solve for this thing over here. So to solve for P, to get P all by itself, we're going to divide by 84.8 liters, and that will cancel, leaving you with just P on the left side. And whatever we do to one side, we're going to do to the other. So N times R times T gets divided by V, which is 84.8 liters. Again, moles will cancel, Kelvin will cancel, liters will cancel, and the only unit that will not be canceled out, that will be left, is ATM, which is our unit of pressure. So in here, I'm going to type this stuff in. So it's 12.2 moles times 0.08206 times 340. Okay, so this is the number that you get when you multiply those all. So I guess 12 times, let's just, unless I typed that wrong, I guess 12.2 times the universal gas constant is very close to 1. Yeah, exactly, it's very close to 1. So then when you times it by 340, you get a number very close to 340. So when you multiply all these numbers on top, it's still very close to 340. We're then going to divide that by 84.8, so divided by 84.8, and we get 4.01. 4.01 atmospheres of pressure. So this has been a video showing practice problems for the ideal gas law, which allows you to solve for pressure, volume, temperature, and the number of moles of gas. And we can do so using the universal gas constant, which is R, which is 0.08206 liter atmospheres over Kelvin mole. Hopefully this has been helpful. Keep working. Good job.